takeoff roll felt normal. That was the problem. At 155 knots, the captain of the MD-82 pulled back on the control column and the nose rose off the runway at Madrid-Barajas, right on schedule, exactly as expected. For approximately 6 seconds, the aircraft climbed. The engines were producing full thrust. The instruments were reading normally. There was no warning, no alarm, nothing to suggest that anything was wrong. And that was the danger, because by the time the aircraft told them something was wrong, it was already too late. The stick shaker fired. The control column began vibrating violently in the captain's hands, the aircraft's final warning of an aerodynamic stall. They were 40 meters above the ground. The runway was already behind them. At that height, there was no recovery the laws of physics would allow. The aircraft rolled to the right and came down seconds later. Of the 172 people on board, 154 lost their lives. The crew were experienced. The weather was clear. The aircraft had been inspected that morning. Nothing about this departure suggested risk. What the investigation would spend 3 years uncovering was not a single catastrophic failure, but a chain of small, ordinary breakdowns building silently beneath the surface. And by the time anyone could see it, every layer of protection had already failed. This reconstruction is based on official investigation findings and recorded data. Madrid-Barajas Airport, Wednesday the 20th of August 2008. Spain was in the middle of a summer heatwave and the airport was operating at full seasonal capacity. Spanair, a Spanish carrier founded in 1988, partially owned by Scandinavian airline SAS, was running scheduled domestic and European routes out of Terminal 4. Flight JK5022 was a routine service, Madrid to Las Palmas de Gran Canaria, roughly 2.5 hours, carrying holidaymakers and residents returning to the Canary Islands. Nothing about the booking list was unusual, nothing about the route was unusual. It was the kind of flight that operated dozens of times a day without a second thought. And that was part of the problem. Because when everything looks routine, it becomes easier to assume that everything is. The aircraft assigned was an MD-82, registration ECHFP, a narrow-body twin-engine jet, part of the DC-9 family, a design that had been in continuous operation since the 1960s. By 2008, it was one of the most well-understood aircraft types in the world. ECHFP had accumulated over 48,000 flight hours. It was not new, but it was not unusual. Thousands of flights like this one departed safely every year on aircraft just like it. On paper, there was no reason this one shouldn't. The crew were not a concern either. Captain Bernardo Garcia Sanchez, 47 years old, held over 10,000 hours of flight experience, more than 5,000 on the MD-82. First Officer José Luis Muñoz Capitan, 38, was also experienced. This was not a junior crew on an unfamiliar aircraft. These were two pilots who had flown this aircraft, on routes like this one, hundreds of times. That detail matters, because what happened that afternoon was not the result of inexperience or a lack of training. It was the result of something far more subtle and far more dangerous. The problems on Flight 5022 did not begin on the runway. They began hours earlier in a maintenance bay with a fault that seemed entirely manageable. The aircraft had arrived at Madrid that morning from Barcelona. During that flight, a warning light had illuminated in the cockpit. The ram air temperature sensor, known as the RAP probe, was showing a fault. The RAP probe is part of the aircraft's air data system, providing temperature readings used in performance calculations. It is not a primary flight control component. Faults like this were not unusual. They were logged. Engineers were notified. A technician began work. At the time, this looked routine. It would not stay that way. To test the system, the technician pulled a circuit breaker, isolating part of the aircraft's electrical system. This was standard procedure. In aviation maintenance, isolating power before working on a system is not optional. It is required. What is also required is that any circuit breaker pulled during maintenance must be returned to its normal position before the aircraft is released back into service. and that this step is verified. At some point during that process, something was missed. Investigators would later focus on whether that circuit breaker had ever been restored. There is no evidence that the technician acted recklessly, or that this moment stood out at the time. That is what makes it so dangerous. It wasn't a dramatic failure, it was an omission. One small step in a routine process, on an aircraft being turned around under time pressure, at a busy airport in the middle of summer. The aircraft was signed off as airworthy, the paperwork was completed, and ECHFP returned to service, with no indication in the cockpit that anything was wrong. But the morning was not finished producing problems. Shortly after boarding, a second warning appeared, an overheat indication connected to the same system. The departure was halted before pushback. Engineers returned. The fault was assessed. A decision was made, using an approved procedure, that the aircraft could continue in service. The crew were informed. The paperwork was updated. On the surface, the issue had been resolved. But beneath that surface, there was now a question no one was asking: whether anything else had been affected in the process. The delay had cost approximately 90 minutes. The passengers were waiting. The schedule was slipping. The pressure to depart was building. And at this point, everything about the situation was pushing in one direction: forward. What no one in the cockpit could see was that one of the systems designed to protect them during takeoff may no longer have been functioning at all. Shortly after 1400, Flight 5022 pushed back from the gate for the second time. The crew taxied to runway 36 left, completed their taxi checks, and lined up for departure. Madrid approach granted takeoff clearance at 14:23. To anyone watching from the tower, this was an entirely routine departure on a clear afternoon. Inside the cockpit, the situation felt different. The crew were working to close out a sequence that had already been disrupted, twice. Not recklessly, not carelessly, but under the kind of low-level pressure that builds after 90 minutes of delays, passenger waiting, and repeated interruptions to a routine they had performed hundreds of times before. And this is where small breakdowns begin to matter. Research into checklist performance shows that interruptions are one of the most reliable ways to introduce error. A checklist that is started, stopped, and restarted does not behave the same way as one completed cleanly. Each interruption forces a reset. Each reset creates an opportunity to lose track of where you were, or to assume that something has already been done when it hasn't. For experienced crews, that risk can become harder to detect. Because when a checklist becomes familiar, the actions can continue even as attention drifts. The words are spoken, the responses are given, but the verification behind them, the moment where you actually confirm what you are seeing, can quietly weaken. Investigators refer to this as expectation bias. You expect the aircraft to be configured correctly because it almost always is. And under pressure, that expectation can begin to replace observation. The cockpit voice recorder captured the crew conducting their checks. The flap item was called. What it could not establish with certainty was whether it was truly verified. And that uncertainty would become critical. Because when the throttles were advanced for takeoff, the aircraft was not configured the way the crew believed it was. The flaps and slats were retracted. The wing was set for cruise, not for departure. Under normal conditions, that mistake would not have made it past the runway threshold. The MD-82 is equipped with a system specifically designed to prevent exactly this scenario: the Takeoff Configuration Warning System, or TOCWS. When takeoff power is applied, it checks whether the aircraft is properly configured. If it isn't, it triggers an immediate, unmistakable warning. Crews are trained to stop the takeoff without hesitation. On every previous occasion where this error had occurred, that system had worked. On Flight 5022, it didn't. When the throttles were advanced, no warning sounded. Investigators would later examine why, and they would focus on something that had happened hours earlier, in the maintenance bay. A circuit breaker had been pulled during routine work on the aircraft systems. Whether that breaker had been restored, and what else it might have affected, would become one of the central questions of the investigation. Because if it hadn't, then one of the aircraft's most important safety protections may never have been active at all. In the cockpit, there was no indication of any of this. The instruments looked normal, the aircraft responded normally, the paperwork said the aircraft was ready. And so, with 172 people on board and no visible reason to stop, Flight 5022 began its takeoff roll. The acceleration felt normal. That is the detail that is hardest to sit with. As ECHFP rolled down runway 36 left, nothing in the cockpit suggested anything was wrong. The engines were producing full thrust, the aircraft tracked centerline, the airspeed climbed through its callouts, 80 knots, 100, 120, exactly as expected. The first officer called the speeds, the captain held the controls. Everything about the departure felt routine. At approximately 155 knots, the captain applied back pressure. The nose rose. The aircraft left the ground. For a moment, it appeared to be flying. What happened next unfolded in less than 6 seconds. The aircraft was airborne with its wings configured for cruise, not for takeoff. The lift available was already insufficient. The margin between flying and not flying had been gone before the wheels ever left the runway. The aircraft was not climbing. It was settling. The maximum altitude reached was approximately 40 meters. In aviation terms, that is not altitude. That is the ground. The stick shaker fired. The control column began to vibrate violently, a physical warning of an approaching stall. In training, this is a recoverable situation. Crews lower the nose, rebuild airspeed, and climb away. But those recoveries depend on one thing: altitude. And here, there was none. There was no time to diagnose the problem. There was no time to respond correctly. By the time the aircraft told them what was happening, it was already unrecoverable. The aircraft rolled to the right. The right wing lost lift first, dropping toward the ground before any input could stop it. Seconds later, it struck the earth. The impact tore the aircraft apart across rough ground beyond the runway. Fuel ignited almost immediately. Fire spread through the wreckage within seconds. Emergency services arrived within minutes. What they found was not an aircraft, but a debris field. Of the 172 people on board, 18 survived. All of them were in the rear section, which separated during the breakup, and became the area where survival was possible. 154 people did not survive. From liftoff to impact, it had taken less than 10 seconds. The first investigators reached the site while the wreckage was still burning. Spain's Civil Aviation Accident and Incident Investigation Commission, the CIAIAC, opened its inquiry within hours. The immediate priorities were clear: recover the flight recorders, secure the debris field, begin speaking to survivors. The cockpit voice recorder and flight data recorder were both found in recoverable condition. What they contained would take years to fully understand. In the first days, the public narrative moved quickly toward the crew. 2 experienced pilots, a misconfigured aircraft, a checklist that had not been completed correctly. Pilot error? It was a simple explanation. The investigators were not satisfied with it. Not because it was entirely wrong, but because it didn't explain everything. The flight data recorder confirmed that the flaps and slats had been retracted throughout the takeoff roll. That aligned with a checklist failure. But it also showed something that should not have been possible. No warning had activated. No horn, no alert, nothing. And that raised a more troubling question. If the aircraft was misconfigured, why hadn't it told them? This is where the investigation changed direction. Engineers began tracing the systems that should have prevented the takeoff. They worked backward through the aircraft's electrical architecture, mapping every component involved in the takeoff configuration warning system. And eventually that path led them back to the maintenance work performed earlier that morning. A circuit breaker, pulled during routine testing. Whether it had ever been restored became a central question, because if it hadn't, then the warning system the crew depended on may never have been active at all. The connection was not obvious. The RAT probe system and the takeoff configuration warning system serve completely different purposes. But within the MD-82's electrical design, they shared a power supply. One fault was visible. The other was silent. And silence, in this case, was critical. The maintenance records were examined in detail. What investigators found was not a single catastrophic mistake, but a pattern. Incomplete entries, missing verification steps, inconsistencies that made it difficult to reconstruct exactly what had been done to the aircraft. No one action stood out as reckless. That was the problem. Because when small gaps exist across a system, it becomes possible for a critical step to be missed without anyone noticing. And that is exactly what appears to have happened here. The investigation widened. CIAIAC began examining Spanair's broader maintenance operation. The inconsistencies found on this aircraft were not isolated. They reflected a larger pattern: documentation gaps, unresolved deficiencies, and verification processes that were not consistently enforced. And the oversight system had seen it. Spain's Aviation Authority, AESA, had identified deficiencies in audits conducted before the accident. Some of those issues remained unresolved at the time of the crash. The system designed to catch the system had also missed something. Another detail drew attention: a previous RAT probe fault recorded on the same aircraft weeks earlier. Investigators examined whether it was connected. It wasn't, not directly, but it pointed to something else. A pattern that had not triggered deeper scrutiny. One question remained. Why hadn't the crew caught the configuration themselves? The cockpit voice recorder captured the checklist being called, but it could not confirm whether the flap position had been truly verified. Investigators were careful here. The evidence showed the checklist had failed. It did not show exactly how. What it did show was the context. The delay, the interruptions, the pressure to depart. None of these factors excuse the error, but they help explain how it happened. The final report, published in 2011, drew a clear distinction. The crew's failure to configure the aircraft correctly was a critical error. But the failure of the takeoff configuration warning system transformed that error into something far more serious. Because under normal conditions, that mistake would not have led to a crash. It would have led to a rejected takeoff, a report, a debrief, and a flight that never left the runway. That distinction is not a technicality. It is the entire point. To understand why the flap configuration mattered so completely, why this was not a minor oversight but something the aircraft could not survive, you have to understand what the wing needed to do in that moment, and what it wasn't capable of doing. Lift is generated by the movement of air over the wing. As the aircraft accelerates, air flows over the curved surface of the wing, creating a pressure difference that produces upward force. The faster the airflow, the more lift is generated. But speed is only part of the equation. At takeoff, the aircraft is heavy, slow, and close to the ground. Under those conditions, a clean wing, one configured for cruise flight, does not generate enough lift to support the aircraft's weight. And that is where this becomes critical. Because without modification, the wing cannot do what is being asked of it. That is why aircraft use high lift devices. Flaps extend from the trailing edge of the wing, increasing its surface area and curvature. Slats extend from the leading edge, improving airflow and delaying stall. Together, they fundamentally change how the wing behaves at low speed, allowing the aircraft to lift off safely with a margin above stall. Without them, that margin disappears. On the MD-82, takeoff requires flaps set between 11 and 15 degrees with slats extended. In that configuration, the aircraft rotates at a speed where the wing can sustain flight. ECHFP did not have that configuration. It rotated with the flaps retracted and the slats unextended. The wing was producing lift as though the aircraft were already at altitude, not accelerating down a runway at 155 knots, which meant that the moment it left the ground, it was already outside the conditions required to fly. The aircraft did not enter a stall after takeoff. It lifted off already inside one. And under normal circumstances, that would not have progressed any further, because the aircraft is designed to stop it. The Takeoff Configuration Warning System, the TOCWS, exists specifically to prevent this scenario. When takeoff power is applied, it checks whether the aircraft is properly configured. If it isn't, it triggers an immediate, unmistakable warning. A horn, a signal that cannot be ignored, a command to stop. On every previous occasion where this error had occurred, that system had worked. On Flight 5022, it didn't. When the throttles were advanced, there was no warning. No horn. No indication that anything was wrong. Investigators would later determine why. In the MD-82's electrical system, investigators determined that the TOCWS and the engine anti-ice system were powered by the same electrical circuit. When that circuit lost power, both systems would have been affected. One of them fails loudly. The other fails in silence. The anti-ice system generates warnings. It creates a fault that is seen, logged, and addressed. The TOCWS does none of those things. It simply stops working. And the aircraft has no way of telling its crew that one of its most important safety protections is no longer there. The crew were not warned, and the absence of that warning removed the final opportunity to stop the takeoff. There is a concept in safety science called a latent condition, a failure that exists inside a system long before it causes harm. Not a dramatic malfunction, not a single reckless act. A weakness that remains invisible because, most of the time, the system around it is strong enough to absorb it. Until one day, it isn't. Spanair Flight 5022 was not brought down by one failure. It was brought down by several. A maintenance process with gaps in its verification chain. An oversight system had identified deficiencies that had not been fully resolved. An electrical dependency that allowed a critical warning system to fail silently. A crew operating under accumulated pressure, performing a checklist in conditions where omission becomes more likely. And, beneath all of it, a final safety layer that appears to have been inactive without anyone realizing it. Remove any one of those elements and 154 people reach Gran Canaria. That is what matters here. Because aviation is not built on the assumption that human beings will never make mistakes. It is built on the opposite assumption that they will. The system is supposed to catch them. Most of the time it does. On the 20th of August 2008, it didn't. What this accident revealed was not just a crew error or a maintenance error, but a more dangerous condition: the invisibility of reliable safety systems. The takeoff configuration warning system had worked for years. Crews trusted it because it had always been there. Maintenance procedures assumed it would be restored because it always had been. Its reliability had become part of the background, not questioned, not verified, simply expected. And when it silently stopped existing, the system had no reflex for that. That is the part worth remembering. Not because it is unique to aviation, but because it is common to every complex system people learn to trust. The things that always work are the things people stop thinking about. Until they don't. In the years after the crash, procedures changed. Circuit breaker management was reviewed. Operators were required to treat the warning system not as an assumed protection, but as something that had to be actively verified before departure. A small step. Seconds to perform. Invisible to the passengers in the cabin. And paid for at terrible cost. The passengers of Flight 5022 boarded that aircraft, believing, quite reasonably, that every layer of protection between them and the ground was in place. They could not have known otherwise. That is what trust in a system means. You board. You sit. And you assume the invisible things are there. On that afternoon in Madrid, one of them wasn't. And no one knew it until the aircraft is already in the air.